So, respected dignitaries around the table, INA fellowships who could join online, or colleagues from BARC, and ladies and gentlemen, good evening to everyone. It's my distinct pleasure to welcome you all to today's evening lecture, organized under the auspice of International Academy of Engineering. INA is deeply committed to fostering dialogue, innovation, and excellence in engineering, and webinars are our platform on our ongoing effort to bring together the academicians, researchers, and industry professionals to deliberate on topics of national importance. So today's topic, changing roles of material in advanced nuclear technologies in India, it's particularly relevant and very timely as our nation is advancing towards the ambitious expansion of nuclear energy program under the Nuclear Energy Mission as well as Vikasit Bharat 2047. So we are honored to have here with us a distinguished speaker, Dr. Raghvendra Tewari sir, distinguished scientist, former director, Materials Group BARC, and senior professor HBNI, who's agreed to deliver the talk on changing roles of materials in advanced nuclear technologies in India. On behalf of INAE Mumbai chapter, we extend a warm welcome to you, sir. May I request Dr. Paulami present a floral bouquet to sir as a token of our gratitude. We are honored to have with us dignitaries, Dover sir, Madam, Shankti Madam, Malhotra and our Chair Balasubramaniam sir, Chairman AARB around here, whose presence truly elevates the stature of this event. Welcome you all, sir, to this event. And we are also a warm welcome also due to the online participants. You can see here GKD sir, and our co-chair Jayesh Bellaraji, as well as Anat Kumar sir, and who could take out time and be with us. Welcome you all to this today's evening lecture. I request Chair INA Mumbai chapter, Balasubramaniam sir, to take it forward with the opening remarks on this lecture.
Respected Dr. Grover, esteemed speaker Dr. Raghvendra Tewari, distinguished INAE fellowships and participants, both here as well as those who have joined online. Greetings and good evening to all of you. Materials, as you all know, which are a part of nature's bounty, and the material science or the metallurgy domain play a vital role in the development and progress of mankind. You can see that this domain has progressed over time to considerable depth of scientific and technical pursuit to bring out various applications, including those for nuclear applications. Usually, for any application, technological application, a cost-benefit analysis is carried out before the deployment. That means the benefit should outweigh the cost. However, there can be some hidden costs, and those may be revealed much later into the application of various nature. The impact on environment and sustainability is one such aspect which needs to be considered in most of the applications, and we are very familiar and we are already facing a lot of impacts. In the context of materials and material science also, this perspective is very important, considering the challenges during material extraction or extracting and processing particularly. So on the one hand, good amount of progress on material development and application are happening, while on the other hand, there are rising challenges regarding sustainability. Now, the context of sustainability, as you all understand, includes ecosystem degradation, the water consumption increase, waste generation, and then their management. So, deciphering such issues and finding solutions before it is too late is very important. Of course, we also know, as technologists or engineers, we also know that once such issues are identified, many solutions can be developed. So in today's talk on changing roles of materials in advanced nuclear technologies in India by our esteemed speaker, Dr. Raghvendra Tewari, I expect that we will get a lot of insight into these perspectives. So once again, I welcome Dr. Tewari. We are very glad that you accepted our invitation. Our means the Mumbai chapter of INAE. And without taking much of your time, we can start directly, or you have anything? Yeah, I will pass on to Dr. Paulami.
Good evening to all present here. It is my honor and privilege to introduce Dr. Raghvendra Tewari. Dr. Tewari has been the former director of Materials Group BARC and is also a senior professor at HBNI. He is also a fellow of the Indian National Academy of Engineering. In his illustrious career, spanning over 30 years, he has contributed to the development of structural and functional materials using advanced microstructural characterization tools. Dr. Tewari joined BARC after graduating from 32nd batch of BARC training school in the year 1989. He did his PhD from IIT Bombay in the year 2000. He served BARC under various capacities in the field of physical metallurgy. He is specialized in refractory metals and alloys, transmission electron microscopy, materials for nuclear reactors, and alloy designing. He extensively worked and guided young scientists, researchers in the field of development of alloys, composites, and intermetallics based on zirconium, nickel, niobium, titanium, and lead lithium. He is the recipient of prestigious Rolls-Royce Research Fellowship from the University of Cincinnati, US, and the Fellowship of Electron Microscope Society of India. He is also the visiting fellow at Ohio State University and University of North Texas. He published more than 210 research articles in international journal and received several national and international awards throughout his career. Some of them include the Young Metallurgist Award from Ministry of Iron and Steel, Scientific and Technical Excellence Award, SRC Fellowship from DAE, the Homi Bhabha Science and Technology Award, and the Metallurgist of the Year from Ministry of Iron and Steel. So with this very brief introduction, I request Tewari sir to kindly begin his talk.
First of all, thank you, Palmi, and thanks to INA for giving me this platform. This topic is essentially a collection of work in the materials group, all the scientists working in the materials group. Not all, means some of them pertaining to lecture. So idea was, in the beginning I wanted to go with a more technical, but then people suggested that it should be more on the general kind of this. So I will keep touch upon certain things. So I will start from the historical perspective just to give the touch of the things, and then move to the topics, and some of the unfinished work will also be covered in that. So with this, let me start. And see, if look, this is my perspective, it may not be correct one. See, 1905, when Einstein gave the concept of the mass energy equivalence, this is where the nuclear energy started. Acha, okay, I'll try. Second is that during in 1920, Professor Aston did some mathematical calculation and showed that if you take the mass of the nucleus as a whole and then you take the sum of the individual proton and neutron, then there is a difference. So invariably the mass of the nucleus was smaller than the small sum of the individual entity. and that he was calling as a missing mass, which later on called as the mass defect. In the beginning, people didn't pay too attention to that because the neutron mass was actually back calculated from the hydrogen mass. And so they thought there was some gap into that, and that is why the problem is. This is a mathematical arithmetic problems are there. However, the race started to find out individually how they measure the neutron, weight of the neutron. And Chadwick was one of the very brilliant person. He not only found out the way to separate neutron, but he very precisely calculated its nuclear mass. When it is done and the calculation was carried out again, then the number change here and there, but the concept of mass defect remain intact. Now this has created the issue. Now question was that if this mass difference is there and if the Einstein theory is correct, then we should have lot of energy to release from the atoms. That is where the concept were developing. And that's why the John Cockcroft and the Ernest Walton, these people are the people who were developing accelerators. The accelerators people, so first thing they did, they taken the lithium atom and bombard proton on that. By bombarding proton, they got release of helium nuclei, which is smaller in size, and there was a release of energy which matched exactly which what predicted by the mass difference and Einstein theory, Einstein relationship. That was first time very firmly people understood that indeed there is a lot of energy is there to unleash if we can somehow break the atoms. And that is where the work started, and very carefully people started working on that. Several scientists, one of the most actually is Hans Bethe, who has developed the mathematical formula. Mathematical formula means proton to proton interaction, proton to neutron interaction, neutron to neutron interaction, then cluster interaction, then the surface energy, then they call the surface tension. All these put together, they found out very close to the nuclear binding energy concept. That is still prevailing today. All the nuclear physicists, if you talk, they will use this formula to predict the energy of the nucleus of the heavy atoms. Then a failed experiment, then a race started actually. If you read history, then people tried to bombard lead with proton to convert lead into gold. And they had done successfully, but this was the costliest gold produced. Okay, but this gave a concept that you can produce heavy atoms. People knew about plutonium, but that time it was in traces. So this Hans and the Statman, they wanted to start a experiment where they first tried with the alpha particle. It failed because uranium is such a heavy atom, the repulsion is very high. They tried with the proton, it didn't work. Then they bombard neutron on the uranium atom, and they were thinking of they will end up with the plutonium. To their surprise, they end up with the bismuth. And that's surprise because then the calculation is started, and it has shown using this Hans model, they had shown that there should be a lot of energy into that. To their surprise, when they recalculated it, it in fact was releasing a lot of energy, and uranium specimen got so heated up, it melted actually. Then they realized it has gone to the melting point and it's melted. So this gave an idea, and just to give you the perspective, 1937 December, when Einstein was moving from Germany to England to go to US. In England, he gave an interview and he said 100 years will take for splitting atoms. And within 2 months' time, Germany split the atom. And that is where everything changed. And then everybody is taken very seriously. And 1939, all the physicists come together, and first time that binding energy per nucleon, what we see in our training school lecture, that was developed, and it has shown that iron is the peak element. And if you go on the heavy atom, they will try to go to iron. If you go on the light side, they will also go to them. And that is where first time fission and fusion concept is started. With this background, why I'm telling you this background, in this duration, Homi Bhabha was the PhD scholar in England, and he finished his PhD in 1939. And he was very much fascinated because all those buzzing activities was going on very close to the England side. And he used to go from lab to lab to find out what is happening and all. 1939, after finishing his PhD, he decided to come back to India to meet his parents and all. Now, to the surprise, to his unfortunate part or fortunate part for the country, 1939 Second World War broke out and he could not go back. He wanted to go as a lecturer there in the universities. He was offered also, but he could not go. So finally he joined ISC Bangalore as a reader. And problem he was facing that his theoretical physics was so dynamic that within 2 months everything was changing. And he was finding very difficult because those days there is no telegram and possible. So only letter used to go, and that too by the steamers, that is the ships. So what was happening, 6 months later he will get the reply. By then the things started becoming obsolete. So he was very much disturbed by that. But Bhabha is Bhabha. He was not bogged down by this thing that he is left out and all thing. He picked up the point from there and he proposed to make the nuclear reactor for the country. And he given a very exhaustive report in Tata and Sons Trust, Tata Trust and the thing. And this extensive report was examined by none other than Dr. D.N. Wadia, who was that time director of AMD. AMD is the oldest institute, older than BRC, older than TFR. So this is the oldest entity of DA. And Wadia said that Bhabha has, your plan has a sort of a natural flaw that India does not have uranium. So your reactor will not run. As per natural phenomena, if you don't have the source of energy, you should not try that. So Bhabha got very upset, but later on they became very good friends. So Bhabha was very upset, and rather he made a very common comment in IC. I think you must have heard that comment, that absence of proof is not the proof of absence. This statement he gave, that you have not dig anything, you do not know how the country is there, and you have already declared India does not have any uranium. So after this statement, he met Pandit Jawaharlal Nehru and gave this proposal. Pandit Jawaharlal Nehru was always supporting very young people and all. So he immediately picked up and found a very young person, 30 years old person, very enthusiastically selling all the idea. So he gave the part of the money, and part of the money came from the Tata Trust, and that is why TFR was formed, where nuclear research started. But then Wadia told him, see, whatever little uranium you can find in the monazite. And those days, all the places from where monazite was present, they were not the part of the regular India after independence. It was still not the part of the India. And that is where he was very desperate. And the worst part was because this monazite was having a lot of ilmenite and rutile. Rutile is used, that is a titanium oxide, which is used for painting, very white painting on that. So in Europe, it was great in it. So 4 or 5 companies, I am showing the diagram over here, from the Kannur onward to Kanyakumari, many these places were there, and nearly we were throwing 3 lakh ton of monazite per year to sending all Europe and other part of that. With this, the total deposited thorium would have been disappeared in 15 or 20 years time. This was the condition, and Bhabha was very desperate on that. So what Bhabha did, so the first thing Bhabha did was that this moment the country became independent, if you see the date, 1 year is not completed. 15 August 1947, we became independent. Within first year, Atomic Energy Act was passed. Within 1 month time, if you see 1 or 2 months time, he was become the chairman of the committee, and the first task he took is to stop the export of monazite. And this was not happened very easily, let me tell you. A lot of fight took place, and before going that, it was this idea was presented by Bhabha, but actually it came from the AMD director, who told him that India has a lot of thorium and how to go to thorium. Now, as a physicist. He worked 4 years it took. 1952 he came out with this model, and that model is still we are working on that. So now what happened, when that's why very disparate attempts were started to get the uranium, because India was not having any uranium. Whatever little uranium was coming, that was coming from the monazite as a part of that. But over the year, AMD materials group and many other groups together, they came together and started working. Now 10 states we have identified various resources. Rather, AMD director is so upbeat. Now he said that tomorrow if you want to start 100 gigawatt, uranium will not be the problem. You may have other problem, uranium supply will not be the problem. Now point is that just I want to give you this general understanding is that 4,000 ton reserve, if you have the reserve or the ore deposit, then only you can economically set up a plant. In India, problem is that except 5 places, as you can see by stars, Jharkhand, where Jadugoda mines is there. If you go to Andhra Pradesh, Tumrapalli is there. And now these two are the running mines. And recently we are started the work on the Karnataka Gogi mines, as in the Rajasthan Rohil mines. Rohil is in a much advanced stage, but there are other sources also possible. Now, for example, in Andhra Pradesh, the figure is showing 93,000, but now we have discovered up to 2 lakh plus. So this is one of the largest deposit. Our only tragedy is that concentration is very low. So I'm talking about the ore, which is starting from 500 ppm and end is 250 ppm. In between, we had to extract the mineral. So at this point, you should remember that. So there are other sources are also possible, and we need to work on that. So what is happening is that what to do with the small sources for that. So long back, we proposed that there are 2 ways to do it. One, because you cannot set up a plant. One is that you make the mobile plant, take it one place, work it out, move to other plant. That activity is still people are contemplating, and they are not going ahead with part of that. But there are other solutions are also possible, that you find a minimum common point where you can extract the ore and bring it. So these are the few issues we still we are all working on that and trying to work out a flow sheet for this. Now with this, I want to tell you this record has not reached so easily. If you look into that, the mineral identification process typically takes 5 years time. The reason is, first we find a tentative region. So that is where literature survey, satellite data, many field research work, they are put together, and then we find a suitable region. When we find something is there, then more costly things comes in. For airborne gamma rays spectrometer or magnetic survey is carried out, lithostructure carried out, petromineralogy carried out, and many other field investigation carried out to figure out really what is happening there. Then this is done not once, it is repeated, done 3-4 times for 3 different agencies, and then all the data is collected together to find out the mineral, find out exactly location of that, and based on that, report is submitted for the mining. Now this is one aspect. Finding ore is one aspect, extracting ore is another aspect, and in that, this is the just picture of that we are showing, that you can see on the helicopter this helical for gamma this catching, and this other magnetic is shown over there. And then you go with the field work, then even you see on the rock, the pen size tells you how fine distribution has been found out and is collected. And then you can go and then you drill a hole to find out what is there underground. This is nearly 50-meter long. This thing cylinders are found. This is on the right picture. Okay, and then you can do the chemical analysis. Now see, not only that uranium trails you get what is the neighbor other rock system and other elements are there. So many of these are worked together. Now from here, mineral processing division takes over, and we try to extract. Now ore is there, then we started extracting. For that, the entire flow sheet is made, and by the time this task is given to UCIL, who will start the concept of mining here. Okay, so what is happening, for example, here, if you can see, that if this is my present ore is there, how to take it out? It is underground ore I'm talking about. Then you have to first make out the exit and entry point. Then some ventilation is required. Finally, you are touching the radioactive material, so ventilation should be very, very strong on that. And then we started making certain pathway for making the machinery to move out. And then slowly we start the vertical shafts and all for the human to move out on this. And Jadugoda now is the deepest mine in India and probably in the world also. I'm not check that point, but in India, this is the after Kolar mine closed down. This is the active close this mine, because we go nearly 1.2 kilometer deep below the surface. So this kind of work starts on that, and then it takes from after the report submitted, it takes 15 years to reach here. The point I was trying to say is that this is a very long time it starts, and we want to start things very by 47 we want one. So ore is there, extraction is a difficult thing. So what happens that now typical, this is the Rohil mine which is underway, and this is the uranium mill in the Tumlapalli, where the materials is taken. So this is the way it starts. You mark the area grossly, then drilling takes place, that how depth you have to blast it off. Then after blast, everything is collected, sent to the top, and then it comes out and the extraction starts. Now extraction has several processes. You need not to worry about that. It generally contains, first of all, it is grinding. So it grinds the materials to a very fine size. Then we take this acid leaching or basic leaching depending on what kind of the ores are there. So for each this flow sheet, MINDI, Mineral Processing Division, works out how much it should be concentration, what should be the duration, what should be the temperature, and all these works are done. Generally, chemical engineering and materials group work together to figure this thing out. And then ion exchange, precipitation, and then come to the MDU process. And in the process, finally, you will see that yellow cake started coming up, and this yellow cake is finally dried and sent to NFC. And in NFC, then the production of the uranium oxide starts. I will not go to that. Now, in this process, what point I wanted to tell is that each site ores are different, and optimization for each mine is needed. For example, in the carbonatite, we require alkaline leaching, which is happening in Tumlapalli. If I go to the Jadugoda side, then it's a granite-based material where you get acid leaching and all. And then this is the process where in BRC people comes on the way, that is materials and chemical group come together to how to optimize to extract the part. Because here if you make a mistake, then uranium will go to the your tailing ponds, which is not good on that side. That is where most of the people work here. And then open pit mine, of course, is there. Some of the places, not everywhere. Open pit mine is much easier things to do. This photograph is from the Jadugoda, and you can see Dr. Vyas is standing there along with other miners there. My point is, which I wanted to say, for small ores, one thing I was telling is making a movable plant. Another is, nowadays, if you see in Kazakhstan, Australia, Uzbekistan, and many other, even in Canada also, what they do is that they do in situ leaching. That is, they pump into the liquid acid or base liquid, whatever is there, the liquid into the ore, into the mine, and allow the water to interact and extract the ore. And then with the pump, they take it out. So what is happening? See, current condition is our ore is 500 ppm. That is, if I take the entire ore out, 99.995 is a waste material for us. So why to energetically, it is not very good idea to take so much of waste for just getting this pump. So that's why our cost of the uranium production goes up. If we start concentrating on this, then what will happen? Only uranium will come out, little bit extra. So 99% material will remain inside, rest you can extract. And that is why we can bring down the cost of the uranium. So this is the another proposal I was trying to pursue further, but it will take some time. After that it will come. The only point here comes in that this ore should be between the two layers. One should be where the bottom layer should be not allowing the your acid to mix with the water bodies and all. So little bit extra analysis is required, and then you take extra uranium out, because uranium has one problem. If you have uranium plus 4 state, it is not dissolvable in anything except in the condition you want to put in. But if it become U plus 6, it becomes soluble in the water. So then it is a dangerous condition for that. So you have to take care of this part. Once we can master this technology, we can bring down the uranium cost very low, and this does not require the entire setting of the plants. So even for the low concentration, small sources can also be exploited. Okay. Now this is where Uzbekistan, they are doing the same thing with this the underground leaching process into that. Now I wanted to take you what is happening in our case. We take everything out, we take the uranium out, what to do with remaining things. So everything ends up with that tailing pond. Now in tailing pond, the size is becoming very, very large over time, and if you want more uranium, it will grow much faster onto that. Now another aspect was to do what to do with tailing ponds. So one concept came up that we can convert into the brick and use that. Some work is being going on, but still it is way required, very way ahead. Things are required to go. Otherwise, if we can convert into bricks and all, this will save a lot of time, space, and earn some money for us. And many time for many radiotherapy, many people, they require this kind of the houses for the
Shielding.
yes. So many kind of things we can use them, but so far not much has moved. But these are some of the issues which are still burning issues are there. Let me move further ahead. Now another component for the nuclear is the zirconium. If you look on the zirconium side, all the properties of steels are superior to zirconium. Okay, only one thing where the zirconium beats the steel is the absorption cross section for the neutron. That is where it actually 12 times it is better properties it offers as compared to steel. So if you do the back of envelope calculation, you will find it gives you two advantages. One, that the thickness of the tube, it allows the designer to play along without compromising too much on the neutron economy. Second, if you go what for the overall irradiation cost of the neutron, because the steel becomes so radioactive, it will be very difficult to handle. So if you calculate all these things, then you find that the higher cost of the zirconium production can be overridden by this. And that is why zirconium was taken, because when in 1980 it was calculated, then the US was finding they are going to lose $150 million per year if they don't go to zirconium and they stick to steel. That is why zirconium came in the front in the picture. But the problem with the zirconium is, moment you put zirconium out, zirconium is highly anisotropic material. And second problem it is having lot of hydrogen related issue. It has very low solubility for hydrogen and immediately forms a brittle phase. So the entire mechanical property of the zirconium alloys get compromised. As a consequence, you have to give a very, very specific orientation to the grains of crystal structures so that you can mitigate them. Now the problem is, the requirement for the hydrogen point of view, hydride point of view, and the irradiation point of view, they don't match really. They rather contradictory to each other. So you have to find an optimum solution and work the steel from there. That is why we had lot of problem in the beginning in making our zirconium alloys, and lot of struggle took place. And what we were trying to mimic is the structure of zirconium. The Canadian materials. This is where the problem started. And this is a flow sheet. I just wanted you to know that on the left side is the double melted, the original old route zirconium alloys were prepared, zirconium 2.59 pressure tube. And then quadruple melted. Then we have gone to the new route where forging was introduced, given by the yellow circle there. So why forging was done, that was one of the point I wanted to just highlight you. And then the other temperatures, let us just forget about those details. Then what is happening, how it was improving the properties. So this radial forging was luckily came for the Bofors guns in Ichhapur, but they were not able to use because that order was not there. So we grabbed that opportunity and gone there and used their press for our purpose, because finally we are also making tubes. The gun cannon is also the tube. So with this idea, we started work on that, and this radial forging started. Radial forging has shown up in the center region where you can see this mouse. This radial forging actually hammers from the fore side and then squeeze the material out. And this gave beautiful properties change into that. The first change was that our property, if you see the mechanical properties, all UTS and all, their deviation came down. It became much narrower as compared to other, what we were having, the trailing side, leading side, they were having a lot of properties variation. Tubes were having a lot of problems. So many of these problems were solved. And microstructurally, what it did, this is the old route where you can see the patches, which has been marked by the elliptical circle. What you can see is that there is a one side of the crystal structure. On the up, you can see another grain size. So there is a variation in the property because of this fine microstructure. So when you have done the forging, these all parts have gone and its structure has become very uniform in the way. As a consequence, our properties, you can see that if you come down, see on the right side, it gives the idea of the fracture toughness, which was 32 in the first tubes made. It is damn low. Now, after all this modification, we have reached to 310. So, which is very close to Canadian quadruple melted. So now 700 megawatt, I suppose that they will perform far better than what we were having the old tubes. Probably we made for 30 years, it should survive 30 years. Keep the finger crossed. Okay, we also changed several things on the composition also. I don't want to go on those details. The size of the alpha grains, the small change in the texture, many such things are done on the way. So with this, let me take you to the next stage of the reactors and all. So one is the rare earth. Now it's a buzzing word, and we were using rare earth by virtue of, I was showing you the picture, because monazite was having the rare earths. So this was an evil thing for us. But now rare earths became the asset and thorium became evil. So that's why the table was turned. So now if you look in your house, every corner, rare earth has slowly sort of percolated in your house. Every corner. You use digital alarm, you use fire alarm, you use fridge, you use remote control, you have the flat screen TV, you have on the phone. You take anything, even this LED, everywhere slowly it has reached. So it has become the new gold material for that. Rather, in one of the speeches, Dr. Monti was telling our old invader, they wanted the gold from Somnath. They didn't know rare earth has higher value. Otherwise, they would have reached up to Orissa. So, rare earth is not a rare earth in factual sense, that ample amount of the rare earth is available on earth. And unfortunately or fortunately, India is not so bad doing on that. Our reservoirs are fifth in the rank. But where China beats us is given here. Is a xenotime is an ore of the rare earth, where light rare earths are 3.5 and heavy rare earths are 96.5. Heavy rare earths are technically, for engineering point of view, are more important than the light rare earth. Whereas in monazite, we have light rare earth 95% and heavy rare earth only 5%. That's why table is turned in favor of the China. And this is the problem we were facing. So what to do? One thing is that, okay, you try improving on that. Second thing is, let us look other side also. So when I taken this task, so we started looking for all the places where rare earth can be found beyond monazite. This is what the story of that. So there are 3 places we had focus on that for the rare earth. One is the Sivana ring complex where rare earth was found. This was done, the entire system was done for the Rohil mines, for the uranium. But in the periphery on the Sivana ring complex, there are a lot of deposits of the rare earths are there, which are basically the volcanic rocks which have come out from the earth to on the top surface. That is rich on that, and they are rich in the heavy rare earths. Similarly, in Gujarat, there is a place called Amba Dongar. In Amba Dongar, this hill is shown. This hill contains Nd metal, that is NdFeB magnets. You require Nd metals. This is the largest deposit of Nd metal in India. So we have immediately grabbed that opportunity. With Gujarat Minerals, we have transferred the technology. Now they are going to set up a small plant there to extract the Nd metal. Now, apart from that, where else we can find? Then lot of searching has shown that coal fly ash also has the rare earths. So we started looking for in all the thermal plants. We used to go collect this thing and did this work. 2 years it's gone. It was done 10 years ago, but people have not paid attention. Then we did it again. And one of the major ones were found in the Neyveli in the Tamil Nadu, where lignite ores are, coals are there. There, if you see in the table given, on the top, work was done in 2011. And after nearly 24, we did it again. And you can see the TRE means total rare earth element available. They are 2200 ppm and 1443 ppm. So it is a very good source of the rare earths. And in this rare earth, heavy rare earths are very, very good. In India, we do not have any known resources for the lutetium. Now, this place has lutetium. And some of my young colleagues are so upbeat, they are telling they can extract up to 1 kg of lutetium per year. If we can really do that, then we will not only give the lutetium isotope to cater all the patients of India, but all across the globe, we will be the biggest exporter of this lutetium. And now europium is another element which we required for strategic purposes. So this is the 2 elements where we were focusing on that. But what I want you to give the attention to, that this is having germanium also, gallium also, and lithium also. All the 3 elements are also important. So when you started extracting, you can extract all these elements also. So we again signed MOU with them, and very soon, I think within 3 or 4 months time, I suppose, the technology demonstration plant will start working there, and we start extracting the material. So the first condition is, first 2 years, whatever product will come, this will come to us. Later on, when they go for the full plant, then it is their property. And so this kind of work I wanted to start on the 2 more places. One is in the near UP and MP border, one plant is there, and another is in West Bengal and this side. So that work is still left before I could start potential, but they also have very good potential. So there are many India resources are there where rare earth can be extracted. We are not so weak on that. My only problem is this is again somebody was telling me that Indians are complicated, Indian ores are also complicated. So this is the problem. So you don't look for one element. Nowadays, this is the policy I made at the time. Whenever you take anything, look the entire periodic table. Something is not useful today, tomorrow it will be. So we nowadays make the exhaustive list of that, and that's why it is taking more time, but it is done. That can be taken care of that. In addition, for dysprosium, gadolinium plants have already been set up. NPC now they get it from this IREL. In addition, ND metal plants has last year been set up in technology was given to Ashwani Magnets in Pune. Now he produces 60 ton per year kind of production capacity he has, and he will produce those metal to make the out. The only problem these people are that these people want to work only in partially. He just want to produce ND metal, didn't want to go all the way to the magnet making. And that is where the problem starts. And then we come to, just like there are two more plants, that is rare earth and titanium theme park has recently been inaugurated just last month by our chairman. So this is having 6 technologically demonstrated plants, where in between commercial and lab scale, you can see that how it is produced, how it is shaped up, so that you can buy the technology and scale it up. So lanthanum, cerium, samarium, and ND metal and titanium, these will be produced there, and that is what we started this part on that. Now let me take little faster. So apart from that, India does not have a known source, primary source for the cobalt, nickel and tungsten. So we have to rely on the secondary sources on that. That is where the work was started, and with the that is our this thing our in the materials group, we started working on this many of these aspects with heavy water boards, and we started producing many of these elements now on the again technology demonstration scale at the RCF place, so that this technology can be taken up to the higher value on that. Now I want to take few more activities here, and one is that we all know that if we want to become independent, VHWR we cannot go to very large number because of the waste produced is too high. We are looking for if we want multiple reactors, then PWR is a slightly better solution because of the waste point of view. If you want to have PWR, you should have the pressure vessel making fabrication technology with us. So that was some work was started, and we started the Bennett. This work was done. We know that this steel was made with the L&T and other team and that. But this is the first stage Bennites, which were used by American in 1960s. So we are mimicking that structure in 2020. But what beyond? So that is where we started the work. See, problem in this is because strength is low, so your thickness should be very, very large. Since thickness is very large, that is 750 mm, you cannot control the microstructure. If you cannot control the microstructure, then you cannot control the properties also. So there will be gradient in the property across the thickness. So idea is to start a material which is strong and tough. So what to do that? So that is where the things come out in the work which was done by Badeshia, Harry Badeshia, was nanobenite steel. In nanobenite steel, carbide is not there. Since carbide is not there, carbide related all the problems are gone. Weldability and all those issues will be relatively solved. And I just wanted to, and when you reduce the size, you increase the strength and increase the toughness also. And this is what happens. So what we are trying to do is that we are refining and maximizing the benite structure so that we impart as much as strength as possible, and then get some retained austenite so that the toughness, that is ductility, is introduced. This is where a lot of work is being done, and for that different alloying additions and many works are being going on. It is only in a very preliminary stage. Probably in 5-6 years time, we will be in the position to come out with a steel which is far superior than present RPV steel. This is my gut feeling is telling, but let us see. Is it RPV in India or anywhere? In India or anywhere. Actually, my personal feeling is that all those submarine Americans are using and Russian are using, they are using this steel. Okay. But this is highly classified, so nobody talks about it. But definitely they are using it because kind of money they pumped in is in $500 to $400 million money has gone into the research of this work. Americans don't do research just for sake of doing the basic research. Okay, so definitely they are doing it. Now this is the steel, you can see this is a 200 nanometers, so grains are in the 100 to 200 nanometers, and thin film of the gamma is given. This is 3D atom probe where one dot represents 1 atoms. So you can see that we have worked out on this. Now I want to draw a strength because our yield strength is same as the western grade steel or eastern grade steel, but you see the UTS. Our nanobenite steel shows nearly twice the UTS value, whereas elongation and yield strength were nearly same. The reason is because the annealing temperature right now my young colleagues have selected slightly higher. I asked them to bring it down to 200. If you bring down to 200, then I am very much sure that yield strength and elongation both will improve upon. But it takes very long time, and nowadays G generation does not have time to wait. So this is the one other way where my young people, they struggle takes place. But this is the work which is still hanging on, and I will take you to the next one, which is molten salt reactor structural material. And in this, we did lot of survey, and with lot of survey on this different US approach, China approach, Russian approach, and even some of the Japanese approach, and put everything together, and we came out with some composition with iteration and worked out how the materials can be processed. So I think Rajiv Kapoor is there, he's the expert in this, so he will tell more about this if you want. But what we were finding that carbon was one of the problem for us, so we reduced the carbon, which has given little bit less strength on that. Otherwise, a lot of carbide were forming, and they were reducing the property of that. Then once you reduce the carbon, then property become beautiful, and now 3 ton steel was melted. It was radially forged in Midhani. Then it's gone for the tube making in NFC. Now we have 3 ton materials ready for making the loop for MSBR. Now, point I want to highlight is this. The designer wanted a requirement of UTS of 690. We are offering 790. They want yield strength 280. We are giving yield strength of 376. They want ductility 40%, elongation. We give 67%. All the properties are 30% above than what their requirement is there. So a lot of headroom is available to play things around. Still, this is not the best. I tell you why. Because had India had a technology of adding tungsten in that.
Lab scale. Lab scale.
No, it is 3 ton, 5 ton materials I'm talking about.
Lab scale. Industrial.
Industrial. It is moved to industrial scale now. So yes, sir. So I'll show. So this materials is qualified for that. Okay. So what we did very quickly from lab, we moved to within 2 years time. We moved from this to this material was never prepared in India. So every step has to be twice qualified by industry process. So that's why it took a bit longer time. Now we have almost the materials ready in all forms. I'm just showing some of the pictures, all forms for going for the MSBR loop making before going for the reactor. But director wants immediately go for the reactor. I do not know. So yes, everything can be made. My only problem is the first time we have made material, I am a bit cautious person. I want it to be first tested in a loop. Yes. In a loop. So all the failures I can see, then I can modify the structure. But he said, "I nothing doing. Your whatever property we wanted, we were demanding, it is meeting. Go ahead." So that is where now things are going on. So now I want to take you to another material, is the carbon-based materials, CNT. So we on the left side, it is this CNT sheet we are making. On the right side, it is a carbon nanotube. Now, CNT, you know that Bhabha Kavach is where CNT is used to reduce the weight along with the boron carbide. So 50% weight can be reduced on that. But what I wanted to tell you that there are carbon nanotube has many other properties which has not been explored yet, particularly carbon sheets. We have recently found out that carbon sheet, because very large surface area as compared to volume, if you can make this material sensitive, they can detect the cancer by coming on the weight, because lot of alcoholic activity starts in the body. They generate this very special chemical, organic chemical on the body. So from your intestine cancer to liver cancer to lung cancer to throat cancer to the your cheek cancer or tongue cancer, everything can be detected just by the blow of one air from your body, because each alcohol has a different component, and that functionality it can identify. Now, idea is we have given to Tata Memorial for testing. They want some 60-70 devices so that they can get a benchmark. So in this process, this material is still in the process. Once it happens, an idea is that you can put a chip, it can go to a village, doctor need not to go, he will blow the things, all the chemical composition will reach to the phone, and doctor can see from Bombay that what is the condition of patient. So this kind of things I wanted to start. I have started little bit, but still it is in the way. So these are the some activities which is completely new and going beyond the general understanding of the material. And this is carbon rod, nano carbon rod, which is again for a strategic purposes they wanted. This is the imported one, and now you see that this is the Indian one, and we have met the property more or less. So many strategic thing where carbon these are required for carbon tubes are required, they can be made out of this. Now for the gas cooled reactors and many others, they want the carbon fiber and silicon carbon composite. That is, matrix is silicon carbide and you have a carbon composite on that, carbon fiber composite. So this technology was also developed. This is made for the gas cooled reactor fuel tube materials. So we have done the work on the right side. You can see this is a nearly I think 1 foot long rod, and this has all the structure into that. And then first the carbon fiber that your skeleton is made preform, and then we make the silicon carbide in sort of infiltrate silicon carbide into that by completely new method. This is not new for NAL CSR, because they were making cap for the this thing ISRO. So we have taken their help and made this material out. But then requirement later on was changed, and they said they want this kind of the material has already been made and it is available with us, and they wanted the silicon carbide fiber should also be made. So now we are moving from carbon fiber to silicon carbon fiber, silicon carbide matrix. For this purpose, India does not have any source of this, and I didn't know it was very costly material. 1 meter costs few lakhs rupees, and our people have produced around 200 meter this silicon carbide fiber, and they kept it on the ground. It left there for some time. Then when I came to know the figure, then I came back to them, asked them to put in the locker at least. So what we did was started from the scratch, because in India you don't get the material. So the most common material, that is monomer dimethyl chlorosilane, we started from there. Then polymerization was done. Then the wire, so you can see the picture on the right side, this wire is cast, that the polycarbonate silicon is in. Then we fire with the green fire is fired, and that's why we get the carbon. The furnace, green color bottom, you can see is a furnace. Is actually the spinning furnace. It has 6 furnaces inside. Each is running wheel into that, and wire pass through that. So different temperature zone, we have different passes for that. And now silicon carbide has been made. We have made ultra high. That is, I don't think except India, US may be having that. That is hafnium silicon mixed carbides are there. They are for ultra high strength, for more than 2300, 2500 degrees centigrade temperatures. They can withhold that. So with this, actually, when we talk about the hypersonic system, then these are the fibers were required for that. So these were developed for that. But right now, I think our Desh Pandey was supposed to give some land so that we can produce in the commercial scale. That is where it is stuck. And then this is another work remaining. Dr. Achana Sharma was there. So I was working with her. Basic idea is that they have this capacitor, high value capacitor. They give a shock, and in the shock, what happens? The material suddenly explodes, and converts into nanometer scale. And then you can have those tungsten nanometer, you can copper, zinc, any materials can be converted into nanometer size powder by this shock. Current problem is that the shock, they generally generate only few of the shocks. One shock does not give more than few micrograms. So I wanted that should continuously produce shocks after shocks so that we can produce at least 100-gram materials to work on. Because idea is to get sufficient material so that I can go for the LAM system, that is near net shape making the system on that. This machine has already been prepared, and in RRCAT, very soon we are going to get, RRCAT is expert in that, so they are making this machine for us. With this, we will get near net shape immediately. If it's a nanoparticle, then your porosity will reduce drastically. As a consequence, your tube will be nearly 99.9% dense material. So you can use and immediately make a shape. Something with a conventional making requires 1 month, it will finish in 3 hours. So that kind of time scale you can reduce on that. But this requires some of this more coordination on our side. Now LAM stands for? That is a laser. Laser prepared. Laser additive. So what is doing is by laser, you are sort of making the pattern into the system. That is powder bed fusion, laser based powder bed fusion. That is LPB. Now I will just couple of slides. I will close the things down. One is that another activity is that in radioactive waste. Okay, uranium is exposed from reactor, brought to the waste management. They take the uranium out. What is the structural happened to a structural material? So what they generally do is that they press and compact it and keep it there. But there is a better way to handle this, is that if I mix nearly 10%, if you see the phase diagram, on the 10 to 15% steel into that. This is also as a product of the radioactive waste. Then the melting temperature comes down a lot. And if we melt them together, we reduce volume at least by 20 times. Okay.
20 times.
Yes. So this volume to this at 20 times we will reduce. But I was going further up, that if we can, along with that, there is called ESR technology, electroslag refining technology. So in that, if we make a slag where all the alpha waste can be contained, then it will reduce further 20 times. So what happens that when you are asking for 100 gigawatt electricity productions, how much waste should be generated? So these are something which we are trying to go for the future. So right now this point has been proven, but electroslag refining part is still little bit difficult to work out. So because we don't have electroslag refiner with us, so either we have to go to SAIL or go to DMRL. So they take their own sweet time to work on that. So you have to go along with their pace. That is where this work is going on. And this is another activity which I started, which is still going on, is we were all struggling for the niobium cavities. We want RRR greater than 300. But to produce RRR 300, I'm telling you that you start with the 1 ton niobium, you will end up with the 200 kg niobium, which is qualifying for that. 800 has to be recycled. So the cost becomes exorbitantly high. So idea is all the currents is confined to the surface. Nothing goes inside. That is the basic property of the electric properties. So what we do is we coat niobium with Nb3SN. Because Nb3SN has a property that if you look on the table, niobium has a critical temperature of 9.2 Kelvin. Nb3SN has a temperature of 18.3 Kelvin. Okay, your superheating magnetic property, you see, you look all the properties, Nb3SN offers much superior properties to that. Now, Nb3SN can be very quickly coated on Nb because the properties are matching quite a bit. And then what we can do is, we can take the materials, Nb3SN thin films out, and then we test the material. So it was tested on the coupon basis by this process. It has already been all the properties have been done, and we are really got all the properties which are matching for us. Now we want to coat it for the cavity. The irony part is we had this idea. Before we implemented, RRCAT gave this idea to the American National Labs, so they have gone for the full assembly coating. So we are left behind now. Now this is the one of the last slide I was telling you. The hypersonic testing was carried out. They want the TZM fasteners because the nose goes to very high temperature in the hypersonic missile system. So this coating was not available in India. So we did this coating. Now this coating was made here with this very special materials, the TZM and coating on that. Now this technology has been transferred to the private company to give it to for the hypersonic or the missiles. And in the end, I want to thank all of you for giving very patient ear to me. And this is the typical group which has worked. You may find that Palmi name is not there because she works on the fusion material. I have not touched the fusion material, so you find some important names are missing. But these are the group people who are working. That there are two things. I could not get the picture of some of them, and that is the one reason. But my idea is that now we should take this is the right time to move to the generation 4 reactor. But before doing that, we should start from the material perspective and then make the country ready for going for that. Rather copying from what US is doing, what Russia is doing, I wanted India should have its own say. That's the way I started 3 years ago. And after supination, this is where I achieved. Thank you very much.
Thank you, sir, for a very inspiring talk, covering a broad spectrum from history to the advanced material and the emerging needs as well. Before we open the forum for further questions, shall I ask, may I request Grover sir to give some impressions on the talk?
Well, it was definitely a very interesting lecture. Dr. Tewari started from historical perspective, how state of Travancore was persuaded to come to India, and the way all those happened. I think all of us have been reading those issues. I think he brought it very nicely through a clip of that movie, which all of us have seen. Moved on to uranium deposit, economic evaluation, in situ leaching of uranium, then moved on to zirconium alloy, then rare earth, and finally materials for pressure vessel, generation 4 reactors, particularly molten salt reactors, moved on to carbon nanotube, and then gas-cooled reactor. I think it was a nice journey covering all the details, and I'm happy that to know that for pressure vessel materials, special attention is being paid. Current steel is Apurva, I think. So moving from Apurva to yet to be deployed, but that has been developed. Then moving to nanobiotic steel is going to be a big development. Yes, so we can see large participants. There may be some on YouTube also. So large participants here also. Good, interesting lecture, and I'm sure that many of these things which we need for the future, particularly molten salt reactor, and you said that your 3-ton material is already ready for loop, and then now loop has to be made, and we may have to have a lot of experience of 2-3 years running, and then moving further on that.
Let me request Professor Shantanu Bandyopadhyay to propose a vote of thanks.
I feel truly honored to propose the vote of thanks. On behalf of INAE Mumbai chapter and on my personal behalf, I extend our sincere thanks to Dr. Tewari, a distinguished scientist, former director of the materials group at BARC, senior professor at HBNI, for delivering such an insightful and enriching lecture. Sir, your talk was truly educational and deeply valuable to all of us. We are grateful to BARC for providing the venue and INAE headquarters for their continued support and coordination. Our heartful thanks also goes to Dr. Grover for his presence and support, and to all participants, both online and offline, for joining us and contributing to the success of this event. A special thanks to Dr. Gopika Vinod for organizing this event. So thank you all once again.